So my name is Lawrie. I work at Antithesis, which means I get to think about autonomous testing all the time. It's really fun. And so I'm going to share a little bit today about what we mean by that. Will shared some about it yesterday at his talk. And as he said, we are all kind of talking about the same thing. You know, you will see some familiar faces in these slides, people in this room. Okay. But first, we're going to talk about The Price is Right. The Price is Right, for those of you who don't know, is a US game show. If you are like me, you may have watched it as a kid when you were homesick at school, or sick from school. It is a game show, and I don't really remember anything, maybe because the only times I watched it were like fever-induced. But I remember like 3 things from it. The first thing is that they called people up from the audience, and people were really excited to be called up, to be told, come on down. The second thing I remember is that you guessed the prices of things. I guess that's why they called it The Price is Right. And then if you were correct, you won the thing, but also you got to play more games to win more things. And for some reason, the only game I remember is Plinko. So if you got to play Plinko, you would go up to the top of these stairs, you would get a disc, and you would drop it. And at the bottom are some numbers, that's money. So if you get the middle, you get $10,000. I think I found it very soothing because it's just fun to watch like the chip fall all the way down. And you know, you might win 10,000 or you might win 0. It's very exciting. So if we take this as my beautiful graphical representation of a Plinko board, so you have the little dots, those are the little pegs that the disc falls between. The boxes at the bottom are your money values, if you will, your outcomes. If I told you, if we were going to play this game together, some of you may know this game as Pachinko. It's a Japanese gambling game. If I told you, all right, there's 3 buckets at the bottom. If you get discs in all 3 buckets, I'll give you $1 million. Think about maybe what you would do. Well, you probably wouldn't just drop 1 disc, right? Because you can't hit 3 buckets with 1 disc. So you would say, all right, I need to drop a bunch of discs, and I want to watch them fall and see what happens. And if you are really an outside-of-the-box thinker, and I think most of you here are, you might think about how can you cheat, or help yourself win by modifying the board. Because you might think, all right, maybe I could add some ramps, maybe I could like add some blockages, maybe, you know, and then you would figure out, okay, we're gonna hit these 3 buckets at the bottom, and then you would win your $1 million. It'd be great. But Lawrie, this is a talk about autonomous software testing. Why are you talking about Plinko? Great question, guys, because I think this is actually a really good model for your software system. If we think about it, these pegs can represent the code execution paths that happen for your system. You can, you know, things enter, your system does things, and then they move on down as it goes. You can think of the disks as kind of the work done by your system that goes through these execution paths. And you can think of the bottom as your outcomes. And now these can be good or bad, right? So good outcomes for your system might be your users do what they want to do. They make a transaction, they create a database, they give you lots of money. These can also be bad outcomes. You lose your users' data. Your system is really slow and they hate you and they never want to come back. We also as software engineers that build perfect code, right? These pegs are predictable. You put things in and they come out the way they expect. But when we test, we realize what we think is a circle is actually a triangle. It's only going to bounce one way. It's not actually going to do what we expect. Also, when we test, we may find out there's actually a black hole over there, and if your system ends up in this state, everything explodes, right? And that's bad. So what is autonomous testing? What do we think about if we keep this mental model of Plinko as our software system? What is autonomous testing? And the first thing is that autonomous testing is not automated testing. So what's automated testing? That's when you have a computer who remembers to run your tests for you, right? And if you are here, you probably have this, right? Like you care about reliability. You're not going to rely on your engineers to remember to run tests for you before they check into main, or so I've told. So that's great. This has been a great step forward in software reliability. You don't have to rely on people to run tests. We let our computers run tests. But autonomous testing means that your computer actually explores the state space of your software as it runs to find the most interesting states. And, well, those are probably bugs. There are other things too, but they're probably bugs, because what's interesting to a computer, what's unexpected. So if we use this metaphor of Plinko, what do we think of as manual testing? So that might be you have a particular part of your code that you're testing, one small part of your system. You drop a disk, you watch what happens, you're happy. As we move to autonomous or automated testing, you have a lot of these tests put together, and maybe a computer drops those disks in for you automatically. You have these outcomes at the bottom that you really care about, that you want to make sure are tested all the time. So you have these pathways that you're testing all the time. This is what your test suites look like. The problem is, of course, that because these are constrained, you are predefining kind of the path that these tests take. You don't notice that this is a triangle instead of a circle, because it can't actually, in the course of this test, you don't give it the opportunity to go outside of the boundaries of the test. And also, there's a whole set of the board that's not even being tested, so you don't know that there's a black hole over there until it happens in production. Okay, so of course, what happens? Well, you think we have to add more tests. And then your test suites look like this. And this is a nightmare. These are really hard to maintain, and at some point, the complexity of maintaining your tests is like more than the complexity of maintaining your software itself. And also, you're still not allowing for that interconnectedness of your system to happen. You're still kind of constraining yourselves into these various paths that you've predefined. Okay, so if you think about what is autonomous testing, well, then we are kind of removing those barriers and allowing our system to exist as it is in the real world, to explore all of the state space, to really understand what's going on in our system from a high level. And it allows us to do things like notice, oh, we have these outcomes we haven't tested. We should probably fix that. Like, we should probably add more tests or do some sort of work in our system to make sure we're hitting all of the outcomes that we care about. Okay, so we all know this. Why should we move towards autonomous testing? We know this. It's really hard to predict everything that will happen to your code when it hits production, especially once you let users in. All right, so here's my question for you. How many of you know someone on your engineering team who uses a tool in a way that you don't think it was meant to be used, and you're kind of impressed that they're doing it that way? Okay. How many of you are that engineer? Okay, that's what I thought. We have seen the enemy, and he is us, right? If this is how we use our tools, why would we expect any less of our users, right? They're going to do things we don't expect. And the reason they do things we don't expect is because every time we create software, we bake assumptions into that software, right? We assume that users will do certain things in a certain way. We assume the shape of their data will look a certain way. So there's a blog post by Patrick McKenzie. You may know him as Patio11 on the internet. It's pretty old. It's called Falsehoods Programmers Believe About Names. And I encourage you to read this. It is fantastic. Go read it. He's a great writer. In this blog post, he lists 40 assumptions that we make about people's names. So the first one, I'm just listing 3. Please go read the rest. So the first one, all these assumptions we make are wrong. People have, at this point in time, one full name by which they go by. Well, that seems like it makes sense, right? Well, unless you have someone who's changed their name legally but uses a different name professionally, like, sorry, you're out of luck. We also assume that people's names fit within a certain defined amount of space. Well, no one really has like multiple first names, right? Or multiple middle names, or we're just gonna ignore all of like, Spanish-speaking countries that have 2 last names. Like, we don't know what to do with you, sorry. And finally, another assumption is that 2 different systems containing data about the same person will use the same name for that person. Well, what if you use a nickname? Are you James? Are you Jimmy? Are you Jim? Are you Jamie? Do you go by your first initial? How do we know? Maybe you even have the same name as someone else in your family. How do we know how to disentangle these people? So this is just this is one field in your data set, right? And these are all the assumptions we're making about this one particular field. Multiply this by all of the assumptions that you're making about all of the fields in your database. That's a big problem space, right? So when we think about autonomous testing, part of what we're doing is we are making explicit these assumptions that we are making about our code. And then we can test these assumptions, and we can recognize when the assumptions that we're making are contradicted by our users or are invalid in some way. So again, if we think about our Plinko board, what are the assumptions we might make about this game? We might think, OK, all disks, if we put them in the top, they end up in a bucket at the bottom. We might think, OK, pegs generate predictable behavior when they're hit. You know, it goes left, it goes right about 50% of the time. Because we have multiple disks in our system, we can make an assumption that disks collide with each other, and we should be able to handle that behavior. And also, we might think, OK, the total number of disks that we have in play are the disks that are at the bottom plus disks on the board. And if we compare this to a software system, we can sort of map some of these assumptions. So if we say all disks end up at the bottom, that means work is always happening, no systems crash, everything makes it through. If we talk about the individual pegs, we can think about, OK, our individual functions, the logic is sound. We handle error cases appropriately. We handle successful cases appropriately. If we think about the disks colliding with each other, that could be we handle concurrency, we handle threads appropriately, we can handle things that are happening at the same time in our system, and everything works out the way we expect. And finally, we can think about maybe some sort of eventual consistency as we think about the total amount of work done in our system. This could be, your data is eventually correct or eventually consistent, so things like that. OK. So how do we move towards autonomous testing? And so this is where we've been talking about this a lot this conference. I think it was Ben yesterday who said, I'm going to tell you what I'm going to tell you, I'm going to tell it to you, and I'm going to tell you what I told you. And so in some sense, I'm going to tell you, or the conference has told you some things already. I'm going to repeat them here so you remember them. And then you're going to go home and be great at this. So the first thing to do is we want to think about building test properties, not test cases. And many of you are familiar with property-based testing, but we'll talk a little bit more about how and why we do that. The second way is to add randomness. We want to let the computer who is running these autonomous tests for us be able to generate things randomly. We don't want to prescribe anything. The third way is we want to validate often. We don't want to just validate at the end. We want to be able to validate in the middle so we can see what's happening. And finally, we want to make sure that we're generating enough work for our system to do interesting things. OK, so what is property-based testing? Which of these statements, if you can say this about your system, which of these statements would you give you more confidence? If you can say, if you have a database, for example, valid records are inserted correctly, always. Invalid records are always rejected. Or what if you could say this? Well, the strings A, B, and C are inserted correctly. Oh, and we also have to do numbers. So these numbers are inserted correctly. Or, well, anything I can think of is inserted correctly, right? If you're writing unit test cases, this is really what you're saying about your system. You're saying anything that I can think of is handled correctly. If we can move towards property-based testing, we are able to make more general statements about our confidence in our system, that it's doing the things we think it should do. Which is why, again, we make assumptions about our code. This lets us explicitly state what those assumptions are. Come on. Oh, OK. Surprise. OK. So like I said, those assumptions for our Plinko game, we could actually turn into test properties. If this was a system, these are the things we would want to assert hold true all the time. These are the things that we would want to test and make sure happen. So you think, OK, this is great. How do I, this is a great conceptual. How do I do it? Well, Zach yesterday gave us a great talk about hypothesis. This is one way to do it. This is an example from their documentation. He already told you all about it. I encourage you to go read it. But the important things to notice, as he said yesterday, are whenever you write a test, you say given, you tell it what are the things that it should be able to accept. In this case, it should be text. And then you say what should hold true about this test, about these functions. So this means you don't have to think, OK, I need to remember A, B, C, longer strings, shorter strings. You can just say, this should always hold true. Okay, so the second topic is adding randomness. In our Plinko system, you kind of have randomness built in because there's the pegs, there's the disks, everything goes randomly. The reason this is so important for software testing is that we want to give control over to the computer to pick things randomly so that we come up with scenarios that we couldn't think of on our own. So if we think of this very basic, very bad unit, no, it's not bad, but it's just incomplete, perhaps, unit test of a very random, a very small database that lets you do a couple things. So you might say, this unit test would look like, insert the key A with the value 1. And then you try to get the key A, you get the value 1. You delete the key A, and then you try to get it again, doesn't exist. This is great, but again, we only know that this works for the key A and the value 1. So what does it look like to add randomness? Ooh, that's exciting. Okay. So what it looks like is we add data generators, and if you use something like hypothesis, you might get this for free. But instead of specifying the key A, we say, okay, generate a key from some range of values. And the value is generate the value from some range of values, and then try doing the same thing with those values instead of specifying them. Your tests will run many, many, many times in their life. And so if you add randomness here, you are covering the entire state space just with one test. You don't have to write it for every case. The important thing about these generators is they should generate valid information, but also invalid information, because you want to test the happy path and the sad path. As it gets repeated, you don't want to just make sure that you accept the things that you think you should accept. You also sometimes want to generate invalid data because you want to make sure that your users are going to generate invalid data, and you want to make sure you can handle that correctly. But even better, so previously we prescribed the order in which these operations happened. And many of you know about fuzzing. So this is where fuzzing comes in. Instead of prescribing the order sequence, what if we just gave our code, or gave the test, here are the things that you can do, and let it choose the order. Because maybe what happens is if you call delete first before you've inserted, oh, we actually don't expect that to happen, and that's really bad. So let you define what you want to do, give it to the fuzzer as kind of your alphabet, and then let it explore, see what happens. And hopefully your code will be even better. The third thing which we can do is validate often. So if we go back to our definition of autonomous testing, a computer explores your software as it runs to find the most interesting states. So how do we think about what is interesting? That's like a very load-bearing word in this phrase, right? So in general, computers can find what is interesting when it's unexpected. And how do we know it's unexpected? We validate often. So if you think about our Plinko example, most traditional testing, you kind of wait till the end of the test to figure out what happened. Did I do everything correctly? Were there any errors? Is the outcome what I expected? But instead, we can think about our properties and validate along the way to make sure our properties are holding during the test. So for example, we might have one of our properties that disks are always making progress down the board. This is something we can check during the test. We can say, oh, outside the board is unreachable. If a disk ever makes it outside the board, that's really bad. We should know about that before the end of the test, right? We can say, this is a really interesting place in our code. We want to make sure we get here sometimes. If we never get here, there's something wrong with our test. And we also, again, it's not bad to validate at the end of the test, right? We want to make sure eventually we get all the disks end up down here. For autonomous testing, these kinds of validations are really important because it gives the computer information about what's happening during the test, which helps us explore states during the test. It can change the states that we're exploring during the test, which just really opens up what's going on during these tests. So what does this look like in real life? Okay. So at Antithesis, we have some SDK assertions that work in many, many languages, and we're adding more all the time. And you can add these, as Ryan was talking about yesterday, in your code itself, which gives us signposts along the way for what's happening. The really cool thing about assertions is that it's kind of a memo both to yourself and to the computer when you're running tests. It's a memo to yourself because you're saying, here is my understanding of what's happening in the system at this time. If your assertions fail all the time, either there's a bug in your code, or if the code is correct, but the assertion is still failing, there's a bug in your mental model of the code. And that's really important to know, because it means there's probably some state somewhere that is wrong, because your mental model of the code is wrong. And so these assertions, if you do it along the way, it helps you figure out, okay, am I actually understanding what my system is doing at every point? So here's an example with an always assertion. So if you have, you get all the keys in your database, you delete them all. If you count it afterwards, that should be 0, right? So we can say this count should always be 0, and you give yourself a nice little detail statement there to help future self not be mad at past self for not helping you out. We have sometimes assertions. So if we have a client request, we want to make sure sometimes the request succeeds. We also want to we might also pair this with a sometimes assertion that sometimes this request fails, and we handle this failure appropriately. And say you have a request, a very basic system. The only 2 states that you should have are OK and fail. Again, very basic, don't code like this. If you get something else out of that request, we call this an unreachable assertion. You should never get here. If you find yourself writing comments that are like, should never get here, I promise this will never happen, turn that into an unreachable statement. So the final thing we want to do is we want to generate enough work in the system. If we only drop 1 disk at a time, we may never explore our system. Or if we do, it will take forever, and it will not actually be helpful to us. So in terms of Plinko, that means okay, we're just going to take an entire bucket of disks and dump it into our system and see what happens. Well, what does this look like for our tests? This is kind of like fuzzing on steroids, maybe. So again, we go back to our assumptions about what our system does. What you should do is just write out all the actions that your system can take. And it's not just individual actions like inserting records, deleting records. It could be larger actions like syncing your database, upgrading your binary. If you have a payment system, you might have individual tests for creating users, creating bank accounts. But you also might have bigger ones for if a user wants to make a transaction, because that's going to require a user, an account, maybe some authorization, maybe you have the corresponding user in your system, so you make sure the money gets transferred from one account to the other. These more complicated tests are the things your users are actually doing. And if you incorporate these other techniques like randomness and things like that, you can actually make sure these happen in a variety of circumstances. Kyle, yesterday, his talk with Jepsen, he spent his whole career doing this, figuring out how to load test or how to create these kinds of combinations and these kinds of conditions for distributed systems. It's really hard, but it's really important, because if we're not actually creating the right amount of combinations and the right amount of conditions, we aren't actually getting to the entire state space. And then we're not actually doing that much better than just unit testing and integration testing. OK. So what are we going to do? Let the change begin at BugBash, right? We think that this is a way that will help you test your code better. And we think you will get better software out of it. And we think you will have more fun writing software. Because remember that picture I had with all what your tests look like if you just keep adding more tests? That's not fun to write tests like that. It's more fun to write tests if you imagine yourself in the position of a user, figuring out what happens in your system. So here's just some options. So we know about hypothesis for property-based testing. You all know about fuzzers. One that AFL is one that is very popular, but I'm sure you all have your fuzzer of choice that you love. Really, look at Kyle's work on Jepsen. It's really, really cool. He's got a GitHub. He shows you what he does. It's awesome. And finally, come talk to us at Antithesis. We love this stuff. We can help you do it. And no, really, go write some autonomous tests. I think it's a spectrum. Autonomous testing is a spectrum. It's not all or nothing. You can make moves towards it, and any move you make towards it is only going to help you. OK. So we found bugs, right? That's the easy part. That's the first 90%. Well, the second 90% is then figuring out what happened, right, when you find a bug. Oh, wait, sorry. Let me do the recap. So if I'm going to give you something to think about, you may have heard this before. Give a man a fish and you feed him for a day. Teach a man to fish and you feed him for a lifetime. But I like this. Give a computer a test and you find a bug. Teach a computer to test and the computer finds bugs forever with no further input from you, right? And as engineers, we're all lazy. And so make this work for you. Make the computer work for you. Now for the bonus round. OK, so you found a bug. Now what? What do you do? With the appeal of unit testing is a test. You write a test, it fails, you know exactly what happened because it is a particular line of code. When you're looking at system failures and system bugs, it's often a little bit harder to understand what happened, especially if it's the kind of thing that requires like 2 or 3 things to go wrong. Or if, like someone mentioned yesterday, you have 2 working systems where the tests pass individually, but when they interact, you get bad behavior. That kind of thing is really hard to diagnose. But what if you had a system where you could actually trace back what happened? You could follow it along the way to figure out, OK, in this failure, what are all the pathways that happened? And what if I could take a step back and test from there and see what happened? What if I could take another step back and test from there and see what happened? What if I could take another step back from there and see what happened? Well, we call this deterministic simulation, because when you test an antithesis, we record everything, the inputs, the outputs, the state of the system at every time. And we can actually do this when we have a demo right out there that you can look at it afterwards for when a bug happens and figuring out what happened actually in the state of your system. So when you combine these things together, it's a pretty powerful tool, right? You're exploring your whole state space, and then when you find a problem, you can actually figure out what happened. So if you would like to know more, please come talk to us, either outside or there is people wearing the Ask Me buttons. You have a lot of experts here about autonomous testing. We would love to take your questions. We love talking about this kind of stuff. I left some time for questions. So if you want to ask questions now, we would love to answer them. Yeah, thank you.